Okay. So first of all, we consider a function with two variables. So for example, we have fx here. Okay, we have fx. Okay, it's a function of nth order of partial derivation exists. So continuous equals domain D, which is center of A and B. So for example, we have f a plus h and b plus k. So in terms of the Taylor's theorems, so it's the first functions, normally the original function fab plus 1 divided by 1 factorials of h alpha x plus k the, delta y of the second factorial the equations plus 1 over 2 factorials of h delta by delta x, so k for delta y, differential n square for f, a, and b. So this one will be continuous until n power of n. So the power of n, the second last of the equation will be 1 to power of n minus 1 factorial, which is h alpha x. This is for n minus 1, okay, and the function. So it will end at this final one, okay, where is 1 to the n power of n factorials. So the equations, then power of n, and the main equations. So this is, for this equation is suitable for theta between 0 to 1. So in here we can introduce a notation of, to simplify this one. So means h alpha divided by alpha x plus k alpha divided by alpha y power of r times the main functions. So this one can be represents is obtained by repeating use of the chain rule. So for the setting of x equals to a plus ht and y b plus kt. So with the range of t from 0 to 1. Okay. So this is how the functions, Taylor functions on these theorems will be expand to gt, from this gt expand to g01. So for factorial of 1 plus t squared divided by 2 factorials of g primes 2 and the rest. So the derivative of g are found in the chain rules, which is g prime is dg over dt, which is dx based on the chain rule, dx over dt times df over dx. So plus dy over dt plus df over dt. So we have learned this one in the chapter 1. So it can be simplified to be something like this lah. H alpha, sorry, delta f divided by delta x plus k delta f divided by delta y. So when you factor the function of s, so it becomes something like this. Okay, for the second derivation, it will be the main function h alpha divided by alpha x plus k alpha divided by alpha y square times the main functions. So in general, the Taylor's theorems is can be simplified something like this, where is g to power of r, okay, means for example second derivation. So this one should be a second derivative. So d to the power of r divided by g times d divided of r. So the main is that function h alpha divided by alpha x plus k alpha divided by alpha y times r, but times the main functions. Okay, so when we put t equal to 1 into the Taylor's expansion of g, so the same method can be used to extend the results of any variables as we mentioned here. So means f a plus h. So this is the first functions. So the summations of from 1 to n, so which is the first functions, okay, plus the 1 over 2 factorials of the second partial times square fa and m minus 1 power of the main function inside, so m minus 1 and fa plus the main functions plus the 1 over m factorials of the main functions times the power of m and the main functions. So this one, okay, this is the main one that you need to understand. So at the end, the Taylor expansions can be simplified from the main function, which is f(x) and y equal to f a and b. A and b is the main original one, plus 1 to the power of 1 factorials, okay, in the bracket of the x minus a alpha to divided alpha x plus y minus b divided by alpha x of the first functions. Then it continues with the second of 1 over 2 factorials, the same function inside, but the power of 2 times the main functions, plus, for example, you have number 3 will be the same one, plus 1 over 3 factorials. Okay, they become the same main function x minus a alpha divided by alpha x, okay, plus y minus b alpha divided by alpha x, okay, sorry, alpha y. Okay, here is times, if 3 factorials times 3, okay, then times with the main function of f a b until the final one is, for example, until 20 factorials, okay, 20 expansions, so it become 1 over 20, which is n, okay, times the main functions, okay, and power of the main factorials n, okay, for example, final is 20, it's become 20 here, so times the main functions. So which this one is, we call it as a Taylor expansions of x as about the point A and B. Okay. So we go for the examples in order for you to see more clear how to use this Taylor series. Okay. For example, example 9.39, to obtain the Taylor series of the function f x y, which is the function of sine x, about point A and B, which is your A is 1 and your B is, for example, your A is 1. This is your A and this is your B. So you have A is 1 and B is pi over 3. Okay. So the question is neglecting terms of degree of 3 and higher. Means your higher degree will be power of what? So the neglecting terms of degree 3 and higher. So the highest degree is power of anybody?
2.
2. Okay, correct. So power of 2, okay. So from here, okay, this is the main the function that based on the Taylor function just now. Okay. So when we include this in term of a and b, so the function will be f x and y equal to f function of, with a and b, a is 1, b is pi over 3 plus 1 over 1 factorials, okay, in the bracket of the x minus 1, y x minus 1, your a is 1, okay. So times the delta over delta x plus y minus pi over 3, 1 over 3. So your b is pi over 3. Okay, this is A, this is B. Okay. Sorry, this is A, this is B. Power of 1 lah. Okay, times the main function of 1 plus 1, sorry, function of 1 and pi over 3. Okay, the second degree order is 1 over 2 factorials. Okay, x minus a, which is 1, alpha over alpha x plus y minus pi over 3, alpha power of 2 times the main functions and the rest. So in this question is only wants you to do until of degree of 2. So in this case, okay, this is your Taylor series. Okay, so since we know that the function of f xy is sine xy, okay, so for f1 when fab or f1 pi over 3, so your answer your is equal to square root of 3 over 2. Okay, so you know, and this is what categorization. Okay, it's quite easy. So for example, sine, you have sine theta. Okay, sine x over y, your x is 1, your y is pi over 3. So at the end you will get sine pi over 3 is, in terms of degree, is 60 degree. So from here you will get in term of you will get a square root of 3 divided by 2. So that's why it's come here. Okay. So okay, in order to do in this Taylor series, you need to fit these things inside of this main Taylor series. So this is your main Taylor series in these questions. So you need to fit each of these equations here. Okay. So in order to do that, okay, you need to do for alpha f divided by alpha x, what happened alpha f divided by alpha y. So here is here, from here. Okay, we need to solve this one. We need to solve this one. Then the second one, we have a power of 2. Okay. So that's why if you have here, so you need to get what is the alpha delta divided by delta x and delta divided by delta y. Okay, based on this function. So in this case, we make it one by one. For example, delta divided by delta x equal to y cos xy. So your main functions is f x y equals sine xy. Okay, this is your main function. So we differentiate, okay, partial differentiate in terms of x. So it will be cos xy. So times differentiation of the inside will be y. So this is the first one. Okay, and we know that delta f divided by difference delta f divided by delta x in the function of a is 1, b is pi over 3. So you will get the main answer here. So then second, okay, we go here. We need to solve this one first. Okay, which is alpha divided by alpha y. Okay, so alpha f divided by alpha y, based on this function, you need to differentiate this one in terms of y. So differentiate of sines xy will be cos xy. Differentiate of xy in terms of y, so you will remain x here. Then we have we include x and y here with the x is 1, y is pi over 3, so we will get 1 over 2 here. Okay, so next is alpha square divided by alpha x square is equals to negative sine square sine xy. So you need to divide this one into the second derivative. Okay, so when you divide this one, you differentiate into second derivative. So differentiation of cos is negative sine xy. Differentiation of xy in terms of x, so you will get y. So that's why you get negative y square sine xy. So when you put it the a and b, 1 pi over 3, you get the third one. Okay, next is alpha square second derivation of f in terms of delta x delta y. So I mentioned this is differentiation of x in terms of y. So this is your main functions. So you need to differentiate this one in terms of y. Okay. So you will get something like this lah. Okay. So you will get something like this. Sorry, second difference. Okay. So then when you include the point A and B, so you will get 1 over 2 minus 1 over 6 pi times square root of 3. Then this is the second derivative of y. Okay, you differentiate this one in terms of y. So you will get negative sine square sine xy. Then you include 1 over pi over 3. You will get this negative 1 over 2 times square root of 3. Okay, once you have these things, what you need to do, you need to include everything in terms of the Taylor series, previous Taylor series. Okay, so f xy, in this case, your xy is sine xy. So we are putting sine xy here. Okay, sine xy is approximates of the first functions, which is function of f in term of 1 and pi over 3. So we already include f 1 over 3 is square root of 3 divided by 2. So 3 divided by 2 plus, okay, second one, you see 1 factorial 1 is 1. So x minus 1, okay, times the first derivative of in term of x. So what happened here? 1 to the 1 power of 1 factorial will be 1 times, okay, del f over del x is 1 over 6 pi, okay, we take from here, okay, times x minus 1, okay. Then we have the second one, y minus pi over 3 times del over del y. So what is del over del y? Del over del y is 1 or plus 1 over 2 del over del y, y minus pi over 3. Okay. Okay, next. Next is, okay, the first term settle, the second term settles. Okay. Then the next is for the second degree, which is 1 over 2 factorial. 1 over 2 factorial is 1 over 2 lah. Okay. Okay, this one is, okay, this one is the first, this one is the second one. Okay. Okay, this is the third one. I mean the power of 2 lah. Okay, the power of 2 until here. Okay, so here, okay, is a plus 1 over 1 over 2 factorial become 1 over 2. Then the first factorial is 1 over negative 1 over 18 pi times x minus 1 square. Okay, so here it comes from here. So you need to what we call it, expand this one. So when you expand this one, okay, what you will get, okay, this one you will get something like this. Okay, so when you expand this one you will get, okay, we go for this term. Okay, what you will get here is plus 1 over 2 factorials times, okay, negative 1 over 18, okay, pi square root of 3, okay, times 2 x minus 1 square. Okay, so then plus, okay, continue here, plus the second one is 1 over 2 minus 1 over pi. Okay, so this one become 1 over 2, okay, minus 1 over 6 pi square root of 3 times x minus 1, okay, times y minus pi over 3, okay, times 2. Y times 2, because based on here, okay, you will be have a this one and expansion, and this one will be times this one and times 2 kat sini. Okay, then minus the third one, actually 1 over 2, okay, times square root of 3 times y minus pi over 3 square. Okay, so from here 2 factorial is 1 over 2, so that's why this one 1 over 2 times the first terms, it become 1 over 30, negative 1 over 36. Okay, the rest remain the same, plus the second term is 1 over 2 times 2 with 2 and cancels, that's why it remains the second term 1 over 2 minus 1 over 6 and until here lah, and minus 1 1 over 2 times 1 over 2 here will be 1 over 4. So minus 1 over 4 square root of 3y over 3. So that's why this one is a simplification of this Taylor series punya expansions. Okay. And final one, this is your final answer. So you need to change the main equations of sine xy in terms of a and b by using the Taylor series of equations here. Okay. So if you have plus 1 over 3, so here will be plus 1 over 3 factorials, the main equation here, okay, times power of 3 f a b. So and the rest lah. Okay, in this case only power of 2 lah. Okay, understand? Yeah, I assume no question is understand. Okay. So what you need to do now, okay, maybe what I can simplify the if you get this type of questions, first thing first is create the series here. Okay. Okay, if a number of 2, number of 2, number of 3, okay. So I can first thing first, you need to create the Taylor series. So in terms of degree lah. In this case 2 degree, so we create this one. Second is okay, change or calculate lah, calculate based on function. Based on function, based on function. So in this case, your function xy, so you get the main original FAB, something like this. Okay. Okay. The third terms is, to make things simplify, is I can say something like calculate lah. Calculate the importance of delta over delta x, then delta over delta y, okay, del over delta xy, okay, del square f, and the rest in order for you to use in your final equations. For the fourth step is plug in. Okay, plug in the Taylor series. And number 5, solve lah, or simplify simplify the equation. So this is the steps that you need to do while using the Taylor series. Okay. Any question? Okay. Okay. So we go for the next topics. Okay, the next topic is about optimization of unconstrained functions. So in these sections, we consider problem of determining the maximum and minimum value of a functions of one variables. So we now turn on our attention on obtaining maximum and minimum functions of 2 variables. Okay. So previously we learned about how to find the maximum and minimum function in one variables. Okay. Normally in maths ones, okay, you learn on maximum, what is maximum, minimums, okay, what is the value of maximums and differentiation, if you remember in the differentiation application. Okay, so then now this will cover on the 2 variables. Okay, so geometrical of 2 variables, for example, we have z equal to fx. So last time normally you learn about f equal to fx equal to function one function one variable fx. Now we have 2 variables x and y. So which always represent of a surface in 3D, 3-dimensional space, which is z being the height of the surface and xy is plane. So xy is xy plane. So remember xy here. So z normally become the height. So this is based on the 2 variable functions. So suppose that f and x has a local maximum value at point A and B, as illustrated in the next figure. So then for all possibilities small value of h and k, if f A or B, that function is higher than f A plus H, okay, or B plus K, okay. So this one H and K is a differentiation of approximation, so that the different increment is a negative value, because of delta f is equal to the main function of A plus H, B plus K minus the original ones. So if f and A is higher than the additional, so delta f is become increments, so it's a negative. Then if you provide that the partial derivation exists and are continuous, by using Taylor's theorem, we can express delta f in terms of partial derivations. So the equations of delta f is h delta f divided by x plus k delta f divided by delta y for a and b for the first factorials, and second factorials is 1 over 2 factorials times t square. Okay, this is the expansion of, this one is the expansion of 1 over 2 factorials h alpha f divided alpha x plus k alpha f divided alpha x square. So this is the expansion, and the rest of the second factorial. What happened in the third degree, third factor, 1 over 3 factorial, and the rest. So where is h and k may be negative or positive numbers. So since h and k are small, the sign of delta f depend on the signs of this one. This is the main functions. So that is the sign of delta f depends on the value of h and k, but the maximum value of function f, x, and y at a and b, the sign of delta f must be negative wherever the value of h and k. So this implies the maximums to occur at a and b, delta f or delta x and delta x over delta y must be 0. Okay. So if f and x has a local maximum of a and b, it's illustrated in alpha b. Okay. So just now here, okay, if a and b is higher than the f a plus h b plus k, so it's a increment value. So this is under figure of 9.18a, and okay, means that the increment maximum value here. Okay, but if a and b is smaller than f a plus h b plus k, so it's a minimum value. Okay, something like this, minimum value. So is the graph will be something like this. And using the above formula, we find the local minimum for occur a and b must be 0. So note this one. If your function is f a b is higher than the function of a plus h, okay, a plus h and b plus k, so this one will be under maximum. But if f a and b is smaller than f a plus h b plus k, so this one will be minimum. Okay, so what happened to saddle point? So how to find the saddle point? Okay, thus the first necessary condition is a maximum and minimum, where is your differentiation is equal to 0 for a and b. Differential of x equal to 0, differential of y equal to 0 at a and b. So there will be a maximum and minimums. So in terms of differentiation, this means that del f df equal to 0, point at which this occur I call stationary point. Okay, so if the df over df and dy is equal to 0, so we call it as a stationary point of the function of the value of functions at those point we call stationary value. So when the conditions of delta f is 1 over 2 factorials of the main functions plus the rest. So where is we putting r equal to del square f divided by del x square, s equal to del f square f divided by del x at del y, and t del square f divided by del y. So when we use this second derivation, okay, this one it can be simplified, okay, simplified to be something like this, whereas we could equally well have deduced there is a minimum of a and alpha square f divided by alpha y square is higher than 0, a maximum at, okay, minimum, okay, this is your summary, this is maximum if this double differentiation of y is greater than 0, and maximum if double differentiation of y is below than or lower than 0, negative value. So this is your main function. In order for you to know is under which conditions, okay, so means that del square f divided by del square x times del square f divided by del square x y, sorry, minus del square f divided by del square x and y square root if below than 0. So we know the conditions, then the sign of delta f depends on the value of h and k and along some path through a and b, and the function have a maximum value which log of path is a minimum value. Such point called saddle point. So in this case of a C is a saddle point. See this one we call it as a saddle point. So where is the maximum for curve C2? C2 become maximum, but C1 it become minimums. For maximums, for the A1 maximum, everything will become maximum. For the B1, everything become minimum, but there is for C1, there is a 2 point where is a C2 become maximum and another one become minimum. So we call it as a saddle point. Okay. So as a summary of this one, of this optimized unconstrained function, okay, number one is a necessary condition for function f and x to have stationary value at a and b is that when you differentiate equal on x, it becomes 0, and differentiate on y, it becomes 0. So in order for you to find this stationary value, okay, you need to differentiate in terms of x and in terms of y at this point. So equal to 0. That's the first things that you need to know, the step number one. Okay, once you have this stationary value, the next question is that stationary point of A and B, is it a maximum of minimum? Okay, in order to do that, you need to do this equation. Okay, you need to test with this equation, which is your second derivative of x, okay, times second derivative of y minus, okay, derivative of x into of y square is higher than 0. Okay, the first condition, and if second derivative of x or second derivative of y is below than 0 at a, b, so we call it as a stationary point too, we call it as a local maximum. Okay, this is the local maximum. Okay, if when we test this point with this equation, okay, we get the first equation is greater than 0, okay, same than 0, but we get delta f divided by delta x square or delta f divided by delta y square is higher than 0. Just now it's below than 0 at point A and B. So this one, that stationary log is, we call it as a local minimum. Okay. Okay, but if these functions is below than 0 at A and B, then automatically we call it as a saddle point. So this is the conditions. And the last one, number 5, if that these conditions is equal to 0 at AB, we cannot draw a conclusion because of the point may be maximum, may be minimum, or a saddle point. Further investigation is required, and it may necessary to consider the third order term of Taylor series. Okay, so this is almost like what you have learned in Maths once. If you remember, in order for you to know that graph, okay, is a maximum or minimum. So what is the point here? So in fact, you have maximum point. You need to differentiate twice. You need to differentiate 2 times. So then you will get the value, then you will get the maximum or minimum. Or you have a that this point, I not remember the terms. Okay, this point. So this is the same concept, but in terms of two functions. So what you need to do first, you need to do the first step, differentiate first x and y. If equal to 0, there is a stationary value. Then you need to use this condition in order to know that point will be maximum, minimum, or saddle point, or cannot be concluded by maximum and minimum and saddle point because of equal to 0. Okay, so we go for the examples. Okay, the question is find the stationary point of the function fx equal to 2x power of 3 plus 6x power of 2 minus 3y(x) power of 3 minus 1 of 3 and determine their nature. Okay, their nature. So there is a three main information. First is a stationary point of this function. This is the main function. The third one is determine the nature. So what you need to do based on the first one, you need to find is it the stationary value. Okay, we know that find the stationary point means that this question already stated that this is a stationary point. So automatically we know that del f over del x is equal to 0 and del f over del y is equal also to 0. Okay. So in this case, what you need to do, you need to differentiate in terms of x and y. Okay, I put back the main function. Okay. Okay, this is your main function. Okay, which is 2x. Okay, I just put it here. Fx y is equal to 2x power of 2 plus power of 3 plus 6xy square minus 3y power of 3 minus 1 over. Okay, so what you need to do first, you need to differentiate this equation in terms of x. So when you differentiate this equation in terms of x, what you will get, 2x power of 3 becomes 6x power of 2 plus 6xy power of 2 minus 150. And the second one, you differentiate in terms of y. Okay, so you will get 12xy minus 9y squared. Okay, for stationary point, both of these partial differentiations are 0. So we know just now I said that there is a stationary point. So we know differentiation of this one equal to 0, differentiation of this y equal to 0. So when you differentiate this one equal to 0, okay, you will get something like this. Okay, so you will get x square plus y square equal to 25. So when this one is equal to 0, so you will get the second derivative here. Okay, so from here you need to find your point. Okay, what is the main coordinate or main point? Okay, from the second equation, which is the second equations, okay, we know that y equal to 0, okay, and fx minus 3y is equal to 0. When we change it, simplify, become 4x equal to 3y. So when we put y equal to 0 in the first equation, we put y equal to 0 in the first equation, okay. So what we'll get, your x is x squared equal to 25. So your x will become plus minus 25. So you know the first term. Sorry. Your first point will be 5. Your x, when x is 5, y is 0, and when x is negative 5, y is 0. So that's your first two main coordinates of this stationary point. Okay, so then the second point, we know that when x equal to 3 over 4y, okay, the second one, when we put in the first equations, so we will get y equal plus minus 4. So the second point, the third point will be 3 over 4 and minus 3 minus 4. So we have 4 points here, which is 5, 0. So we have negative 5, 0. We have 3, 4. Then we have negative 3, 4. Negative 4. Sorry. So we have 4 points here. Okay. Okay. So when we have all these 4 points, what we need to do next, we need to classify the point is a maximum or minimum or saddle point. Okay. So what we need to do, we need to do the second derivative of the main functions. So the second derivative of x become 12x. Okay. So we derive this one in terms of second derivative. So we get second x. We derive this one in terms of second derivative. We get 12x minus 18x. Then we derive this one in terms of y. So we get 12y. Okay. So to make things easy, okay, to make things more clear and easy, we can do this table. Okay. We can do these tables, whereas the first table will be your point. So you have 5.0, 50 point, negative 50 point, 34 point, and negative 34 point. So second column will be the second derivative of 12x. So when you put your x is 5, you will get 60 here. Okay. The third is a second derivative of y. When you put your y is equal to 0, you will get, sorry, your y square is equal to 0. Then 12 times your x is equal to 5, so 60. So the second derivative of y, del square f divided by del x del y square is equal to 0 because your y is 0. So from here, you need to check based on these equations. So the first one times the second one, okay, which is 60 times 63,600 minus the second is 0 square. So automatically you get a positive value. And automatically we know the nature is a minimum. Okay. So you back to this equation, Malik. Back to these equations. Okay. This one minus this one is higher than 0. And your del f is greater than 0. So automatically we know it become minimum. Okay. This one higher than 0. Then your the second derivative of x and the second derivative of y is, or second derivative of y is 0. So it's a minimum. So it's a minimum here. Okay, the value, you just put the main equation with your x and y, you get the main value lah, negative 500. Okay, so for the first point. So we go for second point, negative 5 and 0. Okay, what happened when we change the negative 5, we include the negative 5 in terms of the second derivative of x, we get negative 60. Then we put the negative into this equation, sorry, this coordinate in terms of the second derivative of y, we get negative 60. Then the second derivative of delta x, delta y, we get 0. So back to this equation, okay, this one times this one become positive, okay, minus the 0 square is become positive value, okay. But the nature maximum of minimum, we need to check back here, okay. So the value is higher than 0, okay, correct. But it's under the second one because of the second derivative of x is negative 60, the second derivative of y is negative 60. So it's under the maximum. That's why the nature become maximum. This value you calculate, you just put x and y. So the third terms or the third point, 3, 4. Second derivative, you put it x here, you become 36 is a positive, okay. Second derivative of y, we put 3 of y become negative 36. Okay, the double differentiation of x and y, when you put the value of 3, 4, you will get 48. So from here, you calculate negative 36 times negative 36, positive, become negative value, minus, this is the positive value. So automatically you get a negative value here. Okay, so when it's negative value here, okay, automatically we know that this equation become negative value below than 0 is a saddle point. So we can put the nature of saddle point here. Then this is the main value, calculate. And the final point is negative 3, negative 4. So you get the first negative, the second derivative of y positive, and the derivative of delta x, delta y become negative. So when you calculate based on this equation, you will get negative value. So we know it as a saddle point. Then the value is 300 positive. Okay, so this is on how for you to calculate of the point. So in terms of illustration, the situation of is shown in this contour, okay, of the function of figure 920, okay, this one of these functions. So we can see that in this 5, 0, it become minimum point, okay, minimum point, okay. This is negative 5, 0 become maximum point, and this 2 point become saddle point here, okay, saddle point, saddle point. If you remember in your maths 2, maths 1, so you have that maximum value, you have minimum value, then you have this value. So something like similar, you need to check by differentiation, then you check the conditions, so you need to determine which one. Okay, in this case, this will become maximum. In this case, it become minimum. In this case, this 2 point become a saddle point of saddle point. But saddle point also have a negative and positive here. Okay, so it means that negative, this negative because saddle point, saddle point. Okay. Okay. Do you have any question about this one? Okay, so what you need to know here, you need to understand these steps. Okay, in order for you to do that, you need to first thing first, if you have equations, you need to check is it a stationary or not stationary. If stationary, you differentiate in terms of x, it becomes 0. Differentiate of y becomes 0 at that point. So that's the first step that you need to know in terms of stationary value. Then you need to do it by checking this number 2, 3, and 4, and 5. In order to do that, the easiest way is by doing this schedule, this table. Okay, this is a point. The second term is the second derivation. The third point is the second derivation of y. The fourth one is the second derivation of xy. Then this is the main equation. This one minus this one times this one times this one minus this one square. So you will get what? Then you need to check back the nature of this one. Is it a maximum? Is it minimum? Is it a saddle point? Yeah, clear? Okay. Okay, maybe we have about 2 minutes break, yeah? I will continue. The next topic is optimization of constraint function. Okay. So we have a 2 minutes break. So you can start to gel. Okay. So we have learned about, in terms of this topic, we have learned about the small error. We have learned about exact differentiation. So we have learned about Taylor series. We have learned about optimization of unconstrained functions. The next subtopic is optimization of constrained functions. Okay. So based on the previous exercise, so there are frequent situations in engineering application when we wish to obtain stationary value of the function of more than one variables, okay, for which the variable themselves are subjected to one or more constraint conditions. So these general theories for this application is discussed in the companion text of Advanced Modern Engineering in details. So he will show you the technique of solving. So in order, just now we learned about unconstrained functions. So now it's optimization of constraint functions. Okay, so we go for examples. Okay, so to obtain the extremum value of a function of fx is equal to 2x square plus 3y square, we subjected of constraint of 2x plus y equal to 1. Okay, so the question asks us to find the extremum value of these functions with this constraint. So there is a constraint value. Okay, just now it's unconstrained, so you need to calculate the stationary value. There is no constraints, so you need to find what is the maximum. Is it a maximum point? Is it a saddle point? Is it a minimum point? In this case, the function we have of conditions, where is the constraint is 2x plus y equal 1. Okay, so in these examples, it's easy to eliminate one of the two variables f and y. By eliminating y, we can rewrite of fx and y as a function of this one. Okay, because of we have these constraints, so we can simplify by eliminating these two functions. Variable become one variables. In this case, we eliminate y. So your main functions of f x y 2x squared plus 3y. Okay, we change everything in x form. So when this one x form become y equal to 1 minus 2x. So these functions is included in these main functions, the first equations. Okay, sorry. The first equation. Okay, so the next function of x will become 14x squared minus 12x plus 3. So we can apply for the function of one variables, which we have for extremum value. So when differentiate in terms of x, the first differentiation become 2x minus 12. The second differentiation become 28. So an extremum value occur when f prime x equal to 0. So your x is 3/7, which is your second derivation is higher than 0. So the value is minimum value. You remember this one you have learned in maths once. Okay, your application of differentiation. So what in this question only, and in this question, this type of questions, you simplify from the two variable here, f and xy. So you become one variable become x. Okay, so when you fx, you can use the concept of application of differentiation. Where is yours? First derivation, you can do x minus 12. Second derivation is higher than 0. When higher than 0, automatically we know it's a minimum value. So the extremum is a minimum of this f minimum 3/x when x is equal to 3/7 and y/. Okay, this one is a and direct lah, quite straightforward and easy. Okay, so this is the explanation. In example 9.41, just now, we were fortunate in being able to use the constraint equation to eliminate one variable. So remember here, we are fortunate. So in this case, in some circumstances, in these examples, you can eliminate one of the two variable become one variables. But normally in practice, it's often difficult to have these conditions. Okay, so what happened if you cannot get these conditions? So when you cannot get these conditions, so we consider a problem obtaining stationary point of x, y, and z subjected to constraint of g, x, and y equal to 0. So we shall refer such a point of condition stationary point. So in normal conditions, without the special condition just now, which is you cannot eliminate, we need to use the conditional stationary point conditions. So as a stationary points of f, x, y, and z, so we have a differentiation of delta f divided by delta x times dx plus delta f divided by delta y times dx dy plus delta f divided by delta z times dz equal to 0. Okay, so this implies that the vector of delta f divided by delta x, delta f divided by delta y, and delta f divided by delta z is a perpendicular to the vector of dx, dy, and dz, since g of x, y, and z equal to 0. So when we differentiate dg, okay, partially differentiate it, so it becomes to 0. So thus the vector of dg over delta x, dgy, dg over delta x is a perpendicular to the vector of dyx, dy, and dz. Whereas this implies that the vector of del f, okay, is parallel to the del z differentiation that we can find in search of lambda. So you have a del f into x, y, z minus lambda del g over x and y equals 0, 0, 0. Okay. So geometrically, this means that the level surface object of the objective function f, x, y, and z touch the constraint surface of g, x, y, and z equal to 0 at the stationary points. So this can be neatly summarized by writing the alpha. We use this psi, okay, psi of x, y, and z is equal to the function of fx minus lambda gx, gxy functions. So means that the function of f, x, and y will have a stationary point subject to the constraint of g, x, and y of 0. So the psi of del psi of del x equal to del psi of del y, del psi of del z is equal to 0, with the constraint function of g, x, y, and z equal to 0. Okay, these four equations to determine x and y and lambda for stationary point. The scalar multiple of lambda is called Lagrange multiplier, and the function of psi, x, y, and z called auxiliary functions. Okay. So we go for examples. For example, how these Lagrange multipliers and auxiliary works. Okay. So for examples, we have a function of fx equals fxy equals to 2x squared plus 3y squared. Okay. So subject to the constraint of just now, gxy equal to 2x minus plus y minus 1 equal to 0. So as I mentioned, there is a constraint. That's why the subject is optimization on the constraint functions. So the constraint function is this gx functions. So this is your constraint functions. Okay. So when you have this first equation, the second equation of constraint functions, so the auxiliary functions psi is x, y, z is we use the previous formula, this formula. Okay. So psi x, y, z is equal to fxy minus gxy. Why only xy? Because the functions only fx and y. If you have z's plus z, for example, so you should have z's here. In this case, there is no z's, so only xy. Okay. Okay. So psi is equal to x fxy minus lambda gxy. So what is fxy? So this is the first functions fxy minus lambda gxy is these functions. So you have these functions, auxiliary functions. Function. Okay. So in order to calculate the condition of extrema of f and y, we need to differentiate of del x and del y is equal to 0 when gxy equal to 0. So when we differentiate the psi x over del y, psi y, we get 4x minus 2 lambda. So you differentiate in terms of x. So 2x become 4x minus this one is only remain the lambda. So 2 lambda is equal to 0. This is the first functions. Okay. Then when we differentiate psi to y, we get 6y minus lambda equal to 0. So we get the second functions. And the last one, we get the gxy, okay, gxy, which is gxy, this one, is equal to 0, 2x plus y minus 1 equal to 0. You get the third functions. So you have a 3 equation here. You want to find 3 unknown, which is x, which is y, and which is lambda. So from these 3 unknown, you have 3 equations. Okay. Automatically, you will get the unknown answer of lambda. So from here, this is a simple mathematics. You will get the lambda 6 over 7, x 3 over 7, and y 1 over 7. So that the condition of extrema value of fxy is 3 over 7 and occur at 3 over 7, y 1 over 7. Okay. Okay. So it's clear that the level of curve fxn shown in figure 9.21, okay, after this, that the function have a minimum of at 3/7 and 1/7 in general. However, to determine the nature of the conditions at a point, we have to use the Taylor's theorem just now to consider the sign of fx plus h y plus k minus the fxy function by taking point of 3/7, 1/7, which is say that 3/7 plus h and 1/7 plus k. Okay. So let's satisfy the constraint of 2x plus y minus y equal to 0. So we have 2h plus k equal to 0. So that our k is negative 2h. Okay. Hence, a near point satisfy the constraint of 3/7 plus h, 1/7 minus 2h. So we use the first derivation concept. Okay, which one? This one. Okay. So what happened here is, what you need to do is you need to minus the function of 3/7 plus h, okay, 1/7 minus 2h, minus the original one, f, 3/7, 1/7. Okay, so what is the function of 3h? You use the function of the main function of 2x just now. This is the main function. 2x squared plus 3y squared. So 2x squared, what is your x? Your x squared is 3/7 plus h squared plus h squared plus 3y squared. Your y is 1/7 minus 2h squared. Okay, minus the original one, which is 2 times 3/7 squared minus 3 times y. What is your y? 1/7 squared. So at the end, you will get 14h squared is higher than 0. So since this one is positive, so this point is a minimum. So it's confirmed result of 9.41. So this one is a minimum. Okay, minimum value because of 14h squared is higher than 0. Okay, because square, even you put negative 1 become 1. So 14 is higher than 0. So automatically it become minimum. Okay. So in general, to classify conditions saturation point into maximum, minimum, and saddle point can be very difficult, but the majority engineering application, this can be done using the physical reasons. Okay. So as a summary, if you have questions with the constraints, step number 1, you need to create these auxiliary functions. Okay. Once you have created these auxiliary functions, then you need to use these 3 conditions. These 3 conditions. Sorry, 2 conditions. Del psi over del x, you differentiate into x and y, becomes 0. Then gx and y. So you will get 3 unknowns because we want to find the x, y, and z. What is the main point, and also lambda. So you get 3 unknown, which is x, y, and lambda. And also you get 3 equation of these 3 equation based on this one, 1, 2, and 3. Okay, 1, 2, and 3. So you get 3 equation, 3 unknown. So automatically you will get the answer of lambda, x, and y. Okay. If you have z here, most probably you will have 4 unknown, and you have 4 equation in order for you to solve x, y, z. Okay. Okay. For example, and maybe you have 5 because lambda here. Okay. You have 5 here. So you get the answer of x, y, z, and lambda. Okay. So the 4. 1, 2, 3, 4. 4 unknown, 4 unknown, 4 unknown, and 4. So you will get, if you have a z here, So you get x, y, and lambda. So once you have done the first step of zero function, you find the unknown. Okay. The third one is you need to check the nature of the condition, the nature of the conditions. Okay. So by using these equations, okay, which is this equation lah. So f is the first derivation equation to fx plus delta x, for example, y plus delta y minus f xy. Okay, so when you use this one, okay, so you will get the value. If the value is positive, so it's a minimum. If the value is negative, so this one will be maximum. And if equal to 0, it becomes saddle. Okay, the concept is the same, but the method differentiate skit, some different, little bit change here. Okay. Okay. Okay, that's one of examples. So we go for the next examples. This is application examples. For examples, you have find the dimension of cuboidal box with a top without a top of a maximum capacity whose the surface area is 12 meter cube. So we know that it's a cubicles. So the dimension should be have a cubicles, something like this. Okay, but there is no top here. So you know that x, for example, this is z. So you have x, y, z here. This is x, this is y, and this is z. Okay. So if the dimension of box are x times y and z, okay, the dimension x, y, z. So the dimension become f x, y, z, x, y, z, x times y times z. Okay. But the area of surface area is 12 meter square. So we calculate the surface area xy because of only one, because of the top without top. So xy only one, xy the below part. Okay, the below part here, xy plus 2xz. So x times x, we have 2 here. Okay, so xz plus 2yz is equal to the surface area, which is 12 meter square. So you have first main conditions, main equations, the second constraint equations. Okay, so this is the main equation. Okay, you have a constraint equations here, which is your xy plus 2xx plus 2yz equal to 12. Okay, that's the first step. The second step, you need to do the auxiliary functions. What is auxiliary function? The first function xyz plus lambda, the second function of constraints. This is the second one. So you get the auxiliary functions. Okay. The third functions, you need to find the equations. So the del psi over del x equal to 0, del psi over del y equal to 0, and gxy equal to 0. Okay. In this case, del z, we have another one, del z. Okay. Del z over del, sorry, del psi over del z equal to 0. So the first equation, del psi over del x, we differentiate this one in terms of x. So in differentiate in terms of x, you have yz plus lambda, differentiate of x, the first become remain y, the second remain z, remain the z, third and the rest there is no. So you have the first equations. Then del psi over del y, you differentiate into y, you get the second equations. Del psi over del z, you get the third equations. So you have 3 equations here. Okay, together the first this one you have 4 equations and you have 4 unknowns. Okay, then you solve that equations in order for you to get the results. In this case, how they solve the equations, they are taking x times the equation of 1946 plus y times equation 1947 and plus z times equation 948. Why they want to do that? They want to make sure it become equation under x, y, z. Okay, there is x, y, z for each of equations. So you get these new equations. If you simplify this one, you will get this equation 9.49. Okay, you divide it by 3. Okay, divided by 3, and you get simplify this one. Okay, you will get lambda xy plus 2 divided by 2. Sorry, divided by 2 plus 2xy plus z. So this is this one plus 3 over 2 xyz equal to 0. So from here, you use just from equation 4.9 and 4.5. 4.5, this one. This one, okay, xy plus the area. So when you join both of the equation, you will get the lambda answer, which is lambda equal to 1 over 8 xyz. Okay. So when we substitute this equation, throw up the common factor, so we get 1 minus 1 over 8 xy plus 2z equal to 0. Okay. So then the second equation, this one is improvisation from this equation. Okay. Okay. So you get 1 minus lambda is 1 over 8x, negative 1 over xx. Okay. Y plus x. So everything we divided by y become 1 because everything divided by the x. Okay. For example, here I show you one. Okay, the main equation is del psi over del x is equal to yz lambda y plus 2z, yz plus lambda y plus 2z. Okay, so everything when you put the lambda is 1 over z, so this one become yz minus 1 over 8 xyz. Then the main equation y plus 2z. Okay. So everything is divided by yz equal to 0, equal to 0. So 0. So everything divided by yz. So this one divided by everything divided by yz. So yz divided by yz become 1 minus 1 over 8. What remain? Yz and yz cancels. So it become x. Then y plus 2z equals 0. So that's why you get this one. Okay. Same, man. Okay, that's a 1 minus. Similar method for the second 9.451 equation and 9.52 equations. Okay. So from here, the objective is to find x and y. So from here, so lambda you already get by in terms of x and y. So substitute, subtract in terms of these equations. At the end, you get 1 over 4 yz minus 1 over 4 x z equal to 0. Where is your y equal to x? Okay, y equal to x. Okay, you simplify this one. So when we put in 9.52, so where you get yz equal to 2, and we put in 9.4, you get 1 minus 1 square minus 1 over 2 equal to 0. So you get y square is equal to 4 or y equal to 2. Since y is greater than 2, then x equal to 2. Okay, z equal to 1. So because we already get the 2 here, so we put the in term of the equation, so we get the x. So your answer, you get x equal to 2, y equal to 2, z equal to 1. So when we put it in the main equation, the dimension automatically just now is y, x, y, z. So automatically we know that your x is 2 meter times the 2 meter for your y times the 1 meter for your z. Okay. So, and the follow of physical consideration that the corresponding maximum value since the minimum value is 0. So because this one is higher than 0, so automatically we know this one is a maximum value, because the minimum volume is 0. Okay. Okay. So this is on how another examples. The method is the same. First thing first, you have the main equation. Second, you have the constraint equations. The third one, you need to do the, okay, this is the first one. You need the second one, okay, you need to do the auxiliary function. Okay, auxiliary function. Okay, in order for you to find, okay, order for you at the end of the day here, you need to find what is your x, what is your y, what is your z, and what is your lambda. So how to do it is mathematics based on the equations, simple mathematics. So you just change, substitute. So at the end of the day, the third one you need to find x, y, z, and the fourth one you make a conclusion based on the questions. So there is 4 steps for answer constraint. First, you have the equation, main equation, and constraint. Second, you need to do the auxiliary functions. Third, you need to find the x, y, z by x, y, z, and lambda by doing the differentiation of psi x equal to 0, differentiation of psi y equal to 0, differentiation of psi z equal to 0, and also g, x, y, z equal to 0. So you have 4 equations there. Then you need to solve the equations. At the end, you will get the value of x, y, and z and lambda. Then you need to conclude based on the answer. Okay. Any questions? Okay. So that is the what we call it. Okay, that's for the topic of chapter 2, okay, differential equation. So we have covered total derivation of small error, exact derivative, Taylor theorems, optimization of uncontrolled functions, and optimization of control functions. So this is for the chapter 2. Okay, chapter 2. So I hope everybody clear. Okay. Any question?
No, thank you, doctor.